Hello everyone, welcome to CIS 161. This is C++. My name is Kevin Grems. I'll be your instructor for this semester for this online offering of the C++ class. I believe this is the first time the college has ever offered this class fully online. It's my first time teaching a class fully online, so I appreciate any leniency you can throw my way as I kind of sort through some of the technical details and challenges when it comes to offering an online programming class. Some background, first of all, on me. I work full-time as a software developer. I write .NET and C# code for a construction company in Grettinger, Iowa. That's kind of my day job. I also teach obviously this class and then an additional game development 1 course in the evening on Thursdays. I do live in Spirit Lake, so even though this is an online class, if there ever is a need to get together in person, if there's ever a programming emergency, we could probably make that work depending on kind of the where, what, and why. But that's a little background on me. I guess as far as like going back a little bit farther, I was the guy who originally kind of developed the game design program at Iowa Lakes. So while I'm obviously not your official advisor, if you do have any questions about either programs, computer programming or game design, I'm usually pretty open about answering those questions about the program as a whole, the industry trends, things like this. I can usually be a pretty good resource and point you in the right direction, understanding that kind of the final say is up to your official college advisor. So obviously this is an online class, like I said, fully online, so we'll be utilizing the Canvas learning system heavily throughout the entire semester. We're going to go through a few of the features of Canvas that will help us in facilitating the class. Primarily, lectures, as you can kind of see here, will be given via screen record software. Primarily projecting my desktop, doing some code examples, giving explanations, things like this. And that will be your primary way of receiving content along with the textbook, which we'll talk about in a little bit. Taking a little tour here through the Canvas system, some of the features that we'll be relying on. Let us take a look at the simple syllabus here. We can do it this way. Hasn't fully finished publishing yet. While it's kind of loading up here, I will say that because I was kind of put in this course to lead it kind of last minute, I'd appreciate any leniency you can give me. You'll still get all of the regular course content, learn everything you're supposed to learn for this class. However, it might not be as polished as it could be, and that's again just due to the time constraints. So all the content will be there, but some of the bells and whistles, some of the flashy, like I know the usual teacher of this class is a very fancy sort of Canvas laid out with fancy graphics and things. That's not really going to be possible given our time constraints. So appreciate the understanding there. By way of syllabus, there's not a ton in here. I do leave some of my contact info. Again, my name is Kevin Grems. Here's my email. Email is the preferred way of getting in touch with me one-on-one. This is not my phone number. This is the general college phone number. If you call them, they can put you in touch with me via phone if necessary. We are online, so online office location and office hours are by request. If you do need to, again, kind of meet with or chat with me one-on-one, we can work out those details, preferably via email. The course description for this class needs some improvement, to be honest. We'll gloss over that, keep going down the list here. Microsoft Office 365, yes, that's good. We'll talk more about assignment submission later on. There's kind of a specific procedure and process for submitting your programming projects in this class. You can read through the course objectives. That's kind of the official kind of bullet point list of things that we have to talk about in the class. More on that later. Some kind of official type stuff. Grading scale is pretty typical. You've hopefully seen a grading scale like that before. Methods of instruction, as I said, primarily we'll be using screen recording software to deliver the lectures. That way you can kind of listen to them as many times as you want. You can listen to my nasally drone week after week. Also, by way of methods of instruction, we'll typically be covering one chapter a week. So usually how that will look is I'll release the course content for the week on Sunday evening. That will take the form of a video lecture, video demonstration, and an assignment. So there'll be sort of two components to that. Usually we'll be covering one chapter a week, except for when we get around to midterm time and final exam time. I say final exam, really it's a final project. There are no tests and quizzes in this class. I don't care that you know how to define what a Boolean is or how you can define what a class is. I care that you know how to do it. So you proving to me that you know what you're talking about will take the form of writing code. Very, very project-based. We'll also be utilizing PowerPoint presentation just to kind of guide us through the high points of the textbook. And I do emphasize the high points. Okay, you will be expected to read the chapters of the textbook to get all the juicy details that we simply don't have time to go through, and I wouldn't bore you with through this kind of screen lecture presentation. So you will be expected to read the textbook. PowerPoints are high points only. We'll be doing lots of code demonstrations throughout the chapters in the book. The exception to that would be this first week. There aren't a ton of code examples. We're mainly just going through background information. We'll write a few programs, but they'll be fairly limited for this first week. Yes, grading policies, due dates, and such. I expect assignments to be due when they say they're due. And usually that'll be, if I release the assignment on a Sunday, they'll be due the following Sunday. Really not too many exceptions for this unless you communicate with me beforehand. Communication is key. If somebody comes up to me and asks for an extension on a deadline for an assignment, I don't know that I've ever said no to that extension. The caveat, though, the key point is communicate with me. Communication is key. I need, if your assignment isn't in the Dropbox for that week, I need to know why it's not there, why it's not going to be there well in advance. As much advance notice as you can give. Yes, particularly useful for this class is an artificial intelligence usage policy. I'll just kind of read through this. Students may use AI to assist in the general procedure for how to solve a given problem. Students may not copy and paste code from AI resources into their projects. Key thing there is copying and pasting code. I don't want to see any copy and pasted code from ChatGPT or anywhere else that you might find online, Stack Overflow, things like this. You can use those tools to get a general idea of how to proceed with a problem, or if you need to look up like how do you split a string in C++? How do you tokenize an array? Obviously that stuff you can look up and find the answer to, but the larger problem you will not be able to copy and paste from things like ChatGPT. To kind of test for this, or to check for it, it's really hard to detect if code has been copied and pasted from things like this. So what I'm planning on doing is what I call sort of random code checks, code audits, where from time to time throughout the semester, I will randomly select students and projects and specific lines of code or entire programs where you'll have to explain to me exactly why you did it, what you did, how it works. Basically prove to me that you didn't just blindly copy and paste the code from somewhere else. So full disclosure there. And yeah, attendance, participation. This is an online course. Attendance, participation not recorded or graded. Yes, email is the best way to reach out with questions or concerns if they are on like a one-on-one basis. A couple other tools in Canvas that I would like to use anyway this semester. I hope they're useful tools. In the discussions section, I've created one discussion per chapter of the textbook. We will not be getting through every single chapter of the textbook. there's too many chapters and not enough weeks, and I really don't like doubling up like 2 chapters in a week. So it'll be 1 week, 1 chapter. We have some flexibility if we're all really struggling with a particular chapter, we can slow it down a little bit. But the assumption is when you get to this class, you've had some kind of background in programming already, whether or not that's the intro to programming course, maybe it's like real world programming you may have done. You should be familiar with basic programming concepts and techniques. Discussions. If there is a question you have that you feel that the rest of the class would benefit from seeing, go ahead and ask it here. If you have a question on Chapter 1's assignment, just hit the reply button. You can type your question, and I can reply to it, or other students could reply to it too. We can sort of crowdsource this so that if I'm not able to respond right away, maybe another student can help you out there. So let's utilize this stuff. Let's create like a common source of knowledge for typical questions that students might have chapter by chapter. I've never used this before. I hope it's useful. I hope you've seen it used in other classes. Yeah, we'll cancel out of that. Next up, the assignment section. This is pretty self-explanatory. I will upload the weekly assignments here, again on that Sunday night when I publish the lecture demonstrations. All the assignment files are going to be is just a list, a selection of questions from that chapter in the textbook. And I'm not the type of instructor who, like, if there's 20 questions out of the textbook, I'm not going to assign like 17, 18, 19, and 20, the hardest questions. I don't like that. So what I will do instead probably is kind of spread it out. So there'll be some easy questions, some medium questions, and some harder questions. Again, once we get into Visual Studio, our code editor, I will explain and show you exactly how I want you to submit these things. But for now, just know that here's where you go to see the weekly assignments and where you'll go to upload your work week by week. All right. Discussions, files. I have gone ahead and uploaded the lecture PowerPoints. So these are basically what the video demos are going to be based off of. If you just want to sort of look at the PowerPoint without my nasally drone in the background, go here. You can download the presentations and look at them if you need to. Pages. I know we're kind of jumping around here. So pages are where I will post, first of all, most importantly, the video lectures. So you'll have 1 page per video lecture. I'll kind of embed it inside of the page itself. So as soon as I'm done here recording this, I will create a chapter 1 page, and that is where this video will live. Sort of preliminary type stuff, such as getting Visual Studio set up, I've gone ahead and created a page for that, with just some basic instructions on how to get Visual Studio up and running on your machine. While we're here, we can talk about Visual Studio a little bit. I've already mentioned that Visual Studio is going to be our IDE of choice, IDE standing for Integrated Development Environment. You may or may not have used an IDE in a previous course, in like the Intro to Programming course. I'm not sure if they throw you to the wolves and just have you using Notepad and a Borland C++ compiler. That's how I started. But for us, we're going to be using Visual Studio. It is an industry standard tool. It makes writing C++ code and a lot of different types of code, a lot of different languages and scenarios, makes it a lot easier. We don't have to worry so much about things like missing semicolons or spelling, because Visual Studio will check for a lot of those common types of errors for us. Our quality of life greatly improves when we use an IDE. You can get Visual Studio here at this link that I've copied and pasted, visualstudio.microsoft.com/downloads, and make sure to select the free community edition, which I've circled here in the screenshot. You may, and in fact probably will, have to set up a free Visual Studio account in order to use the software. If you've done this in another class, like the intro class, you can feel free to dig up that old username and password and use it here for this class. There's nothing that's in the professional or enterprise editions of Visual Studio that we will be using. Um, we can get along just fine with the free community edition. I will say, make sure you're downloading Visual Studio 2022 and not Visual Studio Code. Visual Studio is an IDE proper. Visual Studio Code, I know naming, is really just a text editor, a glorified text editor. And I think the download for that is right below Visual Studio 2022. So make sure you're grabbing full Visual Studio, not VS Code. While you're going through and installing it, you'll be asked to select something called a workload that you want to install. You can select whichever ones you want, but for us in this class, the desktop development with C++, again circled in the graphic, is definitely the one you want. That sort of gives us all the tools we'll need to write, compile, and run C++ programs. You can see other examples here, like game development with C++. In the other courses that I teach, Game Dev 2, for example, we use Visual Studio, and we have to have the game development with C++ workload installed. You can do Python development or C# or Node, or game dev with Unity and data science and other types of projects and programs. So just make sure to grab that desktop development with C++. You do need, I would say, an above average computer to install and run Visual Studio. The installation is pretty big, and when you're running it, it is a bit of a memory hog. So if that's a problem for you, if you don't have a computer that you feel will be reliable enough to run Visual Studio, you can always go to the Estoril campus, room 44 and 45, and they have, pretty sure, Visual Studio installed on all of the machines in those computer labs. So anytime those labs happen to be open, you can pop on in and work on your projects, work on your homework. A little note here at the bottom, for ease of grading, I'm requiring you to submit the Visual Studio solution files. Again, we'll talk about what that means a little later. There are obviously other ways to write or edit C++ code, other IDEs like Code Blocks, Bloodshed Dev C++, I think is an old one that I've used. Certainly just good old, like I was saying earlier, good old Notepad, and then a command line compiler. Various ways to write and compile C++ programs. For my sanity and the sake of grading, I want you to submit the solution file. Now, if you really, really are in love with another IDE, you can write your homework in those other IDEs and then just create and copy and paste your solution code over to the Visual Studio side and submit it that way. Also, like I was saying earlier, if you are taking Game Dev 2 next semester, we use Visual Studio in that class. And so getting familiar with it here is only going to help you later on in Game Dev 2. And that's a little tour of Visual Studio setup process. That's pages. We already went through files. That's good. Chat. Occasionally, if a lot of people are having sort of the same types of questions, we may utilize the course chat feature. And this is helpful, like if there's 3 or 4 of us that are kind of all available at the same time and we want more like instantaneous feedback, back and forth conversation, we can use the course chat. We used this way back when COVID was a thing, and I was just getting started using Canvas and the kind of the online tools that it has available with it. And so course chat might be helpful for us later on in the semester. All the rest of this is kind of my stuff. iWillig's Handbook Studio. This is the tool that I use to create and record the video lectures. I think that's about it. Okay, that's enough on Canvas. Let's hop over to something equally as exciting, sarcasm intended, PowerPoint. Okay. Like I said, the PowerPoint presentations are going to sort of guide us through the various chapters within the course. This is the textbook. Because it's an online class, we'll be heavily relying on the structure and format of the textbook to carry us through. A word of caution on the textbook. So it is called Starting Out with C++, Early Objects, 10th edition. There is a similarly named textbook by the same authors called Starting Out with C++, Early Object, or no, it was like basics to functions or something, some other subtitle that's a little bit different. Just know you want starting out with C++, early objects, 10th edition, strawberries. Those delicious looking strawberries on the cover, make sure that's the textbook that you're getting. And that's available, of course, from the Iowa Lakes online bookstore, Amazon, and other places fine programming books are sold. I will tell you, in the video lectures, we'll be utilizing a digital copy of the textbook. Pearson is the publisher of this thing, and they're pretty good about, if you buy the book, you can usually access an online digital version of it. So that lends itself pretty well to demonstrations like this. When you're sitting down and doing your homework, however, when you're reviewing concepts and topics, that doesn't work so well. At least I'm not a fan of digital programming or even IT books. You'll want to get a physical copy. Even if it's used, get a physical copy so you can mark it up, highlight things, flip back and forth without having to sit in front of a computer if you don't want to. Definitely recommend a physical version of the text. And yeah, moving on to a bit of an outline here. So starting to get into course content a little bit. So this is very much an introductory chapter. We got a few more things by way of introduction to go through as far as housekeeping types of things. And then we're going to get into it. So basics, why do we write computer programs? What is computer hardware and software? What are computer programs and programming languages? What is a program made of? I/O, processing, and the programming process. Programming as a process. All right, covered a lot of this, and I'll just make sure that we did, in fact, cover it all. Syllabus, PowerPoints, programming demonstrations. I really like this part. I like the programming demonstrations. You heard me earlier talk about how I don't really care about like key terms and definitions. So we're going to definitely focus more on the demos in the video lessons. I think you'll get more out of it than talking about terms and definitions. Work must be completed within a week, 1 chapter per week usually. Exception is midterms and finals. I will tell you, your final project is going to be a text-based RPG, an object-oriented text-based RPG. So if you even want to start thinking about kind of high-level ideas for a project like that, go for it. You can start thinking about it now. Yes, the course is project-based. Grades are based on completion of the projects, no tests or quizzes. Yeah, I should have said unless they become necessary. I haven't had that happen yet, but if we're really struggling in the class with things like terms and definitions, they're just kind of a stumbling block for us, I may introduce tests and quizzes. Again, it hasn't happened yet. Read the textbook. I mentioned it. We talked about the programming honestly by way of random code audits. We talked about the IDEs. Oh, yes. The course disclaimer. So that's basically, don't expect these video lectures to be like super polished and super high production because again, the time constraints there. Finally, if you want to be my intern, I am open to that. Again, I'm a kind of a full-time software developer as my day job. And I was just informed that if I have an outstanding student who needs an internship, and I know for a fact that the computer programming program and a game design program require some kind of internship, talk to me. I'm not saying we're absolutely going to make it happen, but if you're interested, if you have a good aptitude for this stuff, I would be willing to consider taking you aboard and showing you a few things as far as C# code goes. I write C# during the day. This is a C++ class. Not confusing at all, is it? And I would add one more point here. Why C++? You know, there's a myriad of other languages out there. Why do we focus on C++ so much? I think if it hasn't changed yet, C++ was the language used in your intro to programming course. C++ is not a great beginner-friendly programming language. Languages have come a long way since C++ was invented, and there are many other languages that are better if you're learning a first language like Python, like C#, like Scratch. You're going to see, and we're going to get into the intricacies of what that means, why it is considered a difficult language, especially for beginners. But why do we use it? Why do we have a whole course on C++? Your intro course probably used it. This course will, and certainly the Game Dev 2 course uses it a lot too. It is the industry standard game programming language. And why is that the case? First of all, it can do all the things we need it to do from a game design and game development perspective. Second of all, maybe more importantly, it's fast. C++ code is really, really fast. Almost always, if you write two programs, the same program, one in C or C++, one in Python or C#, the C++ program is almost always going to outperform the others. The reason for this is something called a garbage collection, which we're not going to get into right here, right now. We'll get into that when we start talking about pointers in C++. So it's fast, it's the industry standard, it also happens to not be beginner friendly. So there's a little disclaimer. Okay. Let's talk about some content then. Let me grab my digital textbook. Okay. If you're into using the digital textbook, it kind of looks like this. You get kind of a basic feel for it. We're in chapter 1, section 1, why program? Well, let's see if we can answer that question. Why do we write computer programs? Before we do that, I suppose I should say that I'm going to assume that a lot of this stuff you guys already know. If you have any interest in technology whatsoever, if you've written code before, you kind of already know these high-level points. But just to kind of level set and make sure we're all starting off on the same page, why do we program? Well, what do we write programs for? We write programs for computers, and not just desktop computers, the computers that are in all of our pockets, in our cell phones, in a watch, smartwatch, sometimes in a toaster, or a smart TV, or a smart refrigerator. Our programs are made for computers of various sizes, and the computer then follows the instructions that we write. Computers are dumb. They only do what we tell them to do. And the things we tell them to do are contained in the computer's programming. Program or software. So software is usually like a larger program. If you say program, usually you're referring to a small piece of software, where software contains multiple programs, generally. That's not a hard and fast term, but that's kind of what I found to be true throughout my career. So those things, programs and software, are instructions that a computer follows to perform a task. It does that task and only that task. Computer programs are predictable, where you could say, given the same set of input, they're going to produce the same set of output. That was true for many, many, many years until the inception of artificial intelligence and a concrete example, ChatGPT. So ChatGPT invalidates what I just said, where if you input something into ChatGPT or any chatbot, it very well may output something different. So you're not guaranteed an answer that's the same given your prompt. It's a little confusing, but that's kind of where the AI world is at right now. So what is a programmer? A person with the right skills who designs, creates, and tests programs for computers. And there are some good kind of terms in here. Designs, sort of plans out what they're going to do, what kind of programs they're going to write, actually does the typing of creating the program, and tests the programs for computers. All three very important parts of writing good software, and certainly important points when it comes to being successful in this class. We used to emphasize a lot more the design phase. So like back when I was taking this class, we had to write flowcharts and diagrams and UML diagrams and like plan out in a very high level of detail what the program was going to do like flowchart it from start to finish. That used to be true in the industry as well. You don't see that so much anymore. Designing and planning, that phase is important, but these days we have good enough tools where we can kind of design and plan as we're creating and then iterate on that as we need to. Testing has changed too. So when you think of testing your computer programs, you probably think of like running the program, giving it some input, seeing what works and what doesn't work, and then revising the program and then doing that again. These days, there are good ways to automate the testing of our programs, where you can just write some tests. You're actually writing C++ code to test your C++ code, click a few buttons, and the tests run, and you can see if they automatically pass or fail. That's a little outside of our scope. We'll be doing the first type of testing I was talking about, kind of the manual way. But there is a whole world of testing that can make the programmer's life a lot easier and a lot more sort of correct to ensure that you're solving the problem that you're intending to solve. So without programmers, there aren't any programs. Without programs, the computer can't do anything. So what we're trying to say there is we're kind of a big deal. Programmers are kind of a big deal. Programming, an art and a science. I like this slide. There is artistry in programming. Organization of the tasks that the program performs, how the information is displayed, how the user interacts with the program. So this is sometimes called sort of algorithm design. So I mentioned that the planning phase, the design phase, is a bit downplayed in modern programming, but there still is a little bit of it. So that's kind of what you're doing here. High-level steps that you're going to take and use to solve a problem. How the information is displayed. So this would be called like UI, user interface. You're choosing colors, you're selecting a font, you're configuring your page layout if you're doing web programming. How the user interacts with the program. This is a, let's say, relatively new term. This is called UX, or user experience. So this would be like, how do my navigation menus flow? How is the information on this website structured and organized? We won't do too much of that in this class. We'll be writing what are called console apps, so like text-based programs. We won't be dealing with UI or UX too much. There's a science in programming, so understanding of the language used to write the program and understanding how to test it and to change it if it doesn't work as intended. And benchmarking. So trying to figure out if your program's running really slow, where are those bottlenecks and what can we do to fix them? How fast our code runs is like a very general, generic term, but there's a whole world of computer science involved that allows us to actually scientifically, with math, analyze how fast our code may run in comparison to other code. Way outside the scope of this class, but you'll learn a lot more about that, the computer science part of it, in a computer science program at like a four-year college. Moving right along. Hardware and software. So what is the difference? I hope this is obvious to us. The hardware is the physical components of a computer, and there are various sort of categories of hardware: CPU, main memory, secondary storage devices, and I/O. We're going to go through some examples of all of these. You could probably think of some in your head right now, just with this high-level list. Let's take a look. Hardware categories. Here's kind of some graphics of what we just talked about. So in the middle here, everything is connected to your CPU and utilizes main memory, also known as RAM, random access memory. So key terms, I guess, sometimes people can get confused. If you talk about a computer's memory, we're really talking about the RAM. If we're talking about the computer's storage, we're really talking about things like hard drives, external or internal hard drives, thumb drives, SD cards, again called secondary storage, sometimes also called persistent storage, in that data saved to these secondary storage devices will still be there after you power down and power on the machine. Things stored in main memory, stored in RAM, will not persist when you power cycle the computer. So here you have your inputs, fancy digital camera, like a drawing tablet, scanner, keyboard, of course, webcam. And then your output, various displays. I don't know what. Oh, that's a 3D printer. Definitely an output device. A regular printer, speakers, etc. And then you have your secondary storage. So for the most part, we'll be writing programs in this class that are stored and utilize the computer's main memory. We will be talking about file I/O, so we can write programs that create files that are saved on our computer's hard drives. It's more of a side topic, though. Again, by and large, we'll be utilizing the computer's RAM to store and run our programs. Here's some details about the CPU, so hardware component that runs the programs. In this class, it will run all of our programs. You can also talk about things like GPUs, graphics processing units, which you can write code for. And the GPUs, as you probably know if you've done any gaming, those things are really good at processing geometry and doing math really, really quickly, specifically geometric math, matrix calculations. But the CPU includes a control unit, retrieves, decodes programs and instructions, coordinates computer operations. The ALU performs math much slower, I should say, than the GPU does. Luckily, when we're writing our C++ programs, C++ is a high enough programming language. I said high enough. I wouldn't consider C++ a high-level programming language. It's high enough to where we don't really have to worry about the particular CPU that we're writing code for. If you take a step down from C++ and you start writing what's called assembly code, then you have to start caring about like which type of CPU are you writing your code for. Assembly programming is blazing fast, much faster than even C++. It again is outside of our scope. You can take classes at universities that are dedicated to writing assembly language code. Again, for us, we're lucky that most of this is abstracted. We get to work up a level higher than the CPU. Here's the general CPU cycle. Again, only necessary for us to have kind of a basic understanding of this. So it goes through the fetch, decode, execute cycle. So it gets the next program instruction from main memory, decodes or interprets it, and then executes it, routes the signal to the appropriate component to perform the operation. Going through these slides fairly quickly, again, my assumption is most of us are probably familiar with these concepts. If not, that's okay. If this stuff is sounding kind of strange and foreign to you, you'll especially want to read through chapter 1 of the textbook to get kind of a refresher of computer hardware. Main memory holds both program instructions and data. So main memory, these days computers can have anywhere from 8 to 16 to 32 to 64 gigabytes of main memory. That is insane to me, having grown up in a time when we were lucky to have a computer with 500 megabytes of main memory. So this holds program instructions and data. It is volatile. That's what I was talking about earlier. It is erased when the program terminates or the computer is turned off. It is not persisted. It's also called RAM because the CPU can access data instructions from any memory location. I do have a graphic I'd like to show on page 5. And a drink I'd like to take. Here is how people usually think of main memory. It's essentially rows and rows and rows of, I guess you'd call them cells, like very generically. Each cell of memory has an address. Here they've just labeled the cells with like ascending numerically 0 through 29. As we will come to understand very well later on in the semester, memory is not addressed in this way. Memory is addressed using what's called hexadecimal notation. So for us just starting out, they've given us nice memory labels, location names, but just note that these get a lot crazier. This is just a sample. And then the data actually stored in the memory, that's kind of represented here with the number 149 or 72. You could have a letter or a fraction. Many, many different things can live in the computer's memory. But this is how most people think of it. It's just kind of a sequential list or array of cells that hold data, and each cell in memory is addressed or labeled by a hexadecimal value. Luckily, as you probably have worked with before, we don't have to refer to memory with the hexadecimal labels. We can create our own sort of human-friendly labels for memory, also known as variables. Probably worth talking about bits and bytes. So how is main memory organized? Well, the atomic unit of the computer is known as a bit. And when I read through this slide initially, I learned something. So yes, it's the smallest piece of memory. It is a 1 or a 0. Doesn't get any more fundamental or foundational than that. But here's what I learned. Bit stands for binary digit. Bit. I learn something new every day. Holds an electrical charge. Positive charge is on. Negative charge is off. We can also call this true or false, 1 or 0. All kind of represent the same thing as far as a bit goes. A bit is usually too small to have any kind of meaningful discussion about, so we typically refer to things as bytes. Bit is the atomic unit. A byte is 8 consecutive bits, and it has an address in memory. And there are millions or billions of bytes of memory in a computer. So 8 bits to a byte. Computer people are funny, and they come up with funny names for things. I think 4 bits is called a nibble. Half a byte is a nibble. Like, that's pretty funny. All right, secondary storage. Holds data when the program is not running or when the computer is turned off. Several forms, as we talked about: a disk drive, data stored magnetically or in solid state memory, a flash drive. When I was your age, when I was taking this class, we even stored our programs on floppy drives. Pretty crazy. If you didn't know what a floppy drive is, right here in the PowerPoint presentation, there's an icon that's canonically used to save your files. This is a floppy disk. Flash SD memory, USB flash drive, optical CD or DVD drive. Some computers these days, like the Alienware laptop I'm using to record this thing, doesn't even have a CD or DVD drive. Certainly you could get that on a USB external device, but honestly I've never really needed one. Input devices used to send information into the computer from the outside. There. Many devices provide input like keyboard, mouse, touchscreen, microphone, scanner, camera, disk drive, and they forgot one of the most important ones of all, a gaming controller. So your PS, whatever they're at, PlayStation 5 controller, your Xbox, whatever is the latest one controller. But I do like that they included touchscreen. Touching your phone screen or your tablet screen definitely is input. And other types of input, I would say, you could have like a file input. So if I have, I don't know, a flat text file of employees and salary information, I could input that into a program. The program could parse all of that data and output like an Excel spreadsheet, for example. Also good input. Output, so many devices can be used for output: the computer screen, printer, speaker, disk drive, USB flash drive. For us, our primary output device will be the computer monitor, and it will look like text. So it'll be text in a console application. All right, types of software then. If that's kind of the hardware section, here's some different terms and things when it comes to software. So system software, programs that manage the computer hardware and the programs that run on the computer. Operating systems like Microsoft Windows, Mac OS, Linux. Any Linux users in the house? Manage Manages connections to devices and access storage devices, allow the programs to run. So our programs are going to be compiled and run on probably a Microsoft Windows operating system. If you wanted to run that same program on like a Linux machine or a Macintosh, you would have to recompile the same program on those machines to get that to run. As you probably know, when you write and compile a C++ program, it compiles down to an exe file, and that's the file that you would actually like distribute if you wanted to share your program with someone to just run it. It's what's also known as a compiled binary. It's that little file that you can just double click and that'll run your application. Utility programs support programs that enhance computer operations like virus scanners, data backup, file compression, so like your zip, your 7-zip compression, things like that. Software development tools, how about that? Used by us to create software. Examples are compilers, integrated development environments, and text editors. All right, getting a little more specific, programs and programming languages. We've talked about this. A program is a set of instructions directing a computer to perform a task. A programming language is a special language used to write programs in a very, very structured way, as I'm sure you're all familiar with. Let's take a look at a sample program from the text. Page 9. Here's a good old, oh, that's not even Hello World. Program 1.1, in my opinion, in every programming textbook should be Hello World by convention. This one is not, though. That's okay. This is what a typical C++ program might look like. This is what all program listings in the textbook look like, by the way. So I have like the heading, the program name up here, then the actual code with line numbers. That's pretty helpful and useful. And maybe some questions and answers below it. So this particular program starts with a comment. Then we have some pre-processing directives. We're using our standard namespace. And then we enter into our main function, and then we do the work. We display output, we collect input, we do calculations, and finally we return a value. My hope is that this listing, this program 1-1, you should be able to identify and understand what most of these lines of code are and do. We will discuss them briefly when we do our own Hello World program, but this is a good kind of gut check just to make sure that, yeah, this kind of reminds me of stuff I've seen before. Maybe I can't explain it in high level of detail, but I kind of know what it does at a base level. Notice that the program obviously gets executed line by line from top to bottom. When you start writing classes and object-oriented code, that may not be the case. So, and when you get to writing functions, certainly the execution point can jump around and even into other separate code files. What is an algorithm? A set of well-designed steps to perform a task or solve a problem. Order is important. Steps must be performed sequentially. In the world of social media that we live in, this is a word that kind of everybody, even your mom or your random normie friend, probably knows or has at least heard the term algorithm. This is like when you go to your Facebook feed or your Twitter feed, the godlike algorithm decides what it's going to show you, apparently based on what you've interacted with and what you've liked in the past, though we don't really know exactly how these algorithms work. They're sort of black boxes. At one time I heard that Elon Musk was going to open source the Twitter algorithm. I don't know if that ever actually happened or if people even care about it anymore, but apparently that was a thing. Certainly the Google search algorithm, when you go to Google and search for something, who knows where that data is coming from. So they've definitely black boxed their algorithm. Okay, types of programming languages. Right. I've used the term already here, low level. And when I say low level, I don't mean like bad or it's a lowly, gross dirty low-level language. No, I don't mean that. I just mean which level of abstraction are we working at here? At a lower level of abstraction, we're talking more to the computer's hardware directly, and because of that, it's not very easy for a human to read. So human language and computer language look very, very different. So if you're working at a low-level programming language, you're talking more to the computer directly. As you get higher and higher level, you get closer to human language. And I always like to use the example of like Python programming. When you write a Python program, a single line of Python code, it kind of looks like human readable English, which has its benefits and drawbacks. But there's a table on page 10 that I want to take a look at. Here we go. Some types of programming languages: basic, C, C++. So I should mention C++ has all the features that C has, plus more, plus object orientation. And it offers features not found in C, invented at Bell Labs. C, sometimes people say C#, but it is indeed C#, a language invented by Microsoft for developing applications based on Microsoft.NET. I forget the guy's name, but it was basically a single guy, maybe a couple guys who invented C and C++, whereas C# was kind of developed by a big company, Microsoft. COBOL, Fortran. If you know how to write COBOL code these days, you can make a lot of money because schools don't teach this. It's old, it's gross code, but it just so happens that a lot of like important stuff runs on COBOL. Things like, I don't know, air traffic control software. That stuff runs on COBOL. And when it breaks, there's like one 80-year-old guy living in a mansion that knows how to fix it because they pay him a lot of money to fix it. Anyway, Java, JavaScript used on the web, Pascal, Python, as I mentioned. So the highest level here would probably be like your COBOL, your Python. Your lowest level in this list would probably honestly be your C. They don't have assembly language here, unless it's on the next page. Nope. All right. From a high-level program to an executable file. So when we write our C++ code, that even C++ looks kind of like English. You could maybe show a program to your friends who don't know anything about coding, and they might be able to understand at least some of the math involved. Maybe we still have the common arithmetic operators in C++. So how do we get from that almost English-looking source code down to something a computer can understand? Well, you probably know that that process is called compiling. So first we're going to create a file containing the program with the text editor. We enter some program statements, also known as source code. The file that we're writing in is known as a source file. And like I said earlier, we're going to be using Microsoft Visual Studio to write our code to make our lives a whole lot easier, but you don't have to. Like, we basically get three things that Visual Studio will do for us automatically when we click the button to run the program. It's going to compile, link, and execute our source code for us. If we didn't have Visual Studio, you could do all those steps sort of separately via command line, but who wants to do that? Just another source for error and headache. So we write the code basically in a source file. We run a preprocessor to convert the source file directive to source code program statements. And I'll explain what that means in our demo program. I think back on page 10. No. Yeah, back on page 9. We had something up here. Maybe this looks familiar to you. # include IOStream. So that's like a separate package of code that exists within the C++ language that we didn't have to write, that we're sort of importing to use in our program. That allows us to do things like cout, cin. So cout, if you didn't know, displays output to the user. Cin allows the user to provide input to the program. So type in text and save it away in this hours variable. Probably getting ahead of myself there. So we do that, and then we run the compiler to convert the source program statements into machine instructions or machine code, which is stored in an object file. And while the C++ source files are human readable, we can more or less understand what they are. We're programmers after all. If you were to look inside of an object file to look at the machine code used to run the program, you would not have a clue what is going on, and you're not supposed to. The computer is supposed to understand that. Then we run the linker to connect hardware-specific library code to machine instructions and ultimately produce an executable file, so that exe file that you can double-click and run and see the output of your program. And lucky for us, all these steps, well, really B through D, are going to be performed by a single command or button click in Visual Studio. Here's kind of a visual. If you wanted to see all the flow from start to finish. So when we write code, we're going to be writing code in a text file called hello.c, well, whatever your file name is, .cpp. CPP standing for, of course, C++. So we write the code here. It goes through the process that we just talked about. Ultimately, we end up with an OBJ file, and you can see the OBJ file in your Visual Studio project folder structure. We can look at it later, I guess, if we want to. But then the linker takes that and then turns it into an executable. So many software development systems that provide an IDE, but any good IDE should have the following. Should have a text editor. Duh, we have to have a way to write the code. Should have a compiler. Should have a debugger. So the debugger would allow us to do things like step-by-step execute lines of code one by one and look at the state of our variables as we're executing the code line by line. Visual Studio definitely has a debugger. Other supporting utilities like, like a performance analyzer. So the software I write at work is very, very large, and it does have some bottlenecks. So to help us identify what those bottlenecks are, the IDE, Visual Studio, has a performance analyzer that will tell us which functions are causing the application to slow down. We won't need that in this class, but those tools do exist. Those tools, by the way, exist in the other paid versions of Visual Studio. So you're going to get those in your professional version and your enterprise edition. And a user interface, a UI that ties them all together. And Visual Studio definitely has a UI. So what is a program made of? Common elements, most programming languages, things like keywords, programmer-defined identifiers, operators, punctuation, and syntax. And lucky for us, so another benefit of using an IDE is that when we're writing our code, these language elements are oftentimes highlighted in a very specific way. So your keywords, your language-specific keywords may be highlighted in blue. So you can't use that word like if as, say, a variable name. Variable names are another language element that get their own kind of highlighting in your IDE. Let's take a look. We'll fire up a real program at the very end of this, so you can see the syntax highlighting in the IDE in action. Here's another just sort of sample example program. Similar, but not exactly the same as the one we saw earlier. Keywords here would be like using, namespace, include, int. In fact, most of this program is keywords because it's such a small basic program. Cout, return. We do not get the line numbers here. We don't get any syntax highlighting. It turns out in PowerPoint is not a great way to display code. All right, keywords, also known as reserved words, have a special meaning in C++, cannot be used for other purposes like variable names. They are lowercase. As we talked about earlier, here's some examples. Programmer-defined identifiers. are made up by the programmer. There's a whole like art and science to creating your variable names, basically, is what we're talking about here. Not part of the C++ language, used to represent various things like variables, memory locations. An example of that from the previous slide would be like num1, num2, sum. Those are all programmer defined. Let's take a look at page 16. Here. So that same sort of graphic of the memory that we saw earlier, we have the individual cells that will contain the data, and then the little number in the box, which is like that memory's address here. So we know that the value 72 is stored in memory location 23. But memory location 23 doesn't really mean anything to us. So instead, what we can do in our code is create these sort of arbitrary identifiers called length. And so we can say length points to 72 at location 23 in memory. Here's the common arithmetic operators. I hope you guys are aware of these already. If you want to add, use the plus sign. If you want to subtract, use the minus sign. The asterisk is multiplication, and this forward slash is division. Assignment is the equal sign, single equal sign, by the way. Double equal sign means something very different and will cause you to have agony and pain if you use a double equal sign where you should have used a single equal sign. All right. Here we have a variable called num2. We're assigning equal to it the value 12. Here we have a variable called sum. We're assigning to it the value of the num1 variable plus num2. So punctuation, I would like put this in double quotes, punctuation. Punctuation is stuff we have in English, like a period or an exclamation point. But it's a character that marks the end of a statement or that separates items in a list. In this case, like, here's the items in a list, so double num1 equals 5, comma, this should all be on one line. Why we insist on writing code in PowerPoint presentations, I don't know. Here, this is a little bit better. So you have a double num1 equals 5, you have a double num2, a double sum. And here's then saying num2 equals 12. Line numbers, so this is useful. Certainly in Visual Studio we have line numbers. If you have a compiler error, for example, it will tell you more or less which line number contains the error, and sometimes what to do to fix the error. If you're having trouble with a programming project or an example program in the textbook, it's often helpful to say, hey, Kevin, what are they doing on line 4? I don't understand line 16. Can you explain that to me a little bit more? Can you break that down? So in your source code file, a statement is an instruction to the computer to perform one unit of action. It can contain keywords, operators, programmer-defined identifiers, and punctuation. It may fit on one line, or it might occupy multiple lines. So here's a single statement that uses 2 lines. The dead giveaway here that it is a single statement is that we end in a semicolon. So in C++, all statements end in semicolons. You could also write it like this. Keep it all in a single line, if you can. I think that's way more readable than what was there earlier. Okay, as we kind of round out the presentation, at least, I know, like I said, we're going a little bit quicker through some of the preliminary material. Future presentations will contain much more code, much more hands-on demonstrations. So don't let this first presentation be an indication of how the rest of the term will go. There'll be a lot more hands-on to come. But rounding out the presentation, variables. So a variable is a named location in computer memory. Instead of referring to memory locations by their cryptic-looking hexadecimal addresses, we can give meaningful names to our memory locations. that usually describe what is being stored there. So a variable holds a piece of data. The data that holds may change while the program is running, and it probably will. The fact that it is a variable, vary, means that it will change as the program is running. The name of the variable should reflect its purpose. It must be defined before it can be used. Definition can include the variable name and the type of data. So we've been seeing these examples so far like double num1. So num1 is the name of a location in memory that we're getting ready to put some data into. By the way, we don't know where in the computer memory this variable is going to go. The compiler handles that for us. I should say the operating system handles that for us. That's one of the things that's abstracted away from us as sort of high-level programmers. Not only do we say that that's the name of the location in memory where we're going to store some data, we also say that the type of data we're going to store there is called a double, or like a fractional piece of data. We're going to talk more about data types later on, but know that this is something called a data type. We're saying what type of number is num1 going to be. That's going to be a fraction. Could be a fraction, could be an int, which is like a positive or negative whole number. And there are various other data types that we'll encounter as we go through. Boiled down into its simplest sort of process, all programs follow this three-part procedure. Looks like something has gone awry with the numbering scheme. There. That's better. 3 steps that many programs perform. I would say probably all. Most. Gather input data from the keyboard or mouse from files on disk drives, process the data, and then output the results of the processing. Send it to the screen or a printer, write it to a file, rinse and repeat over and over again until the task is accomplished. Program process. Define what the program is to do. That part, good news, will be done for you. So this is going to take the form of like your chapter projects. I will tell you what the program is to do. You have to do it. Visualize the program running on the computer. This is like some weird Zen type stuff. Not weird, but it's kind of weird sounding for a PowerPoint like this. Visualize what it's going to do. Boom. Use design tools to create a model, hierarchy of. Here's what we're going to do here. Boom. Sometimes pseudocode can be helpful. I've used pseudocode before. I can tell you, in my years working in this field, I've never used a flowchart. When I've sat down to write some code, I've never used a flowchart. I have used, however, pseudocode, and if that word sounds scary, it's really not that bad. Pseudocode is just sitting down with like a Microsoft Word document or even just a pen and paper and just writing out in English the steps that you're going to take to solve the problem. Not anything resembling C++ or Java or Python code. You're just kind of brainstorming the sequence of steps that you're going to do to solve the problem. Once you get that down, once you're comfortable with the pseudocode you've written, then it's just a matter of translating the pseudocode into real actual C++ code. Check the model for logical errors. Write the program source code. Can you tell I'm like a very practical, pragmatic sort of meat and potatoes kind of guy here? Here's my process. Define what the program's going to do. Maybe write some pseudocode. Write the program source code and then compile it. Again, some of the stuff about visualizing and spending tons of time designing the program, that's like old stuff. That's the way we used to do things. It's a method of coding called the waterfall, where you spend all this time up front thinking about things and not really writing any code. And you get all your requirements set in stone. It's very rigid and flexible. Then you write the program, and then usually it doesn't work, and you have to go back and redo the planning phase again. These days we're a lot more agile. That is a term that's thrown around a lot in the software development world, where you're like changing and adapting as you're writing the code. As you're writing the code, the requirements may change, and that's okay. You just adapt and overcome. And kind of rinse and repeat until the problem is solved. It's a lot more nimble. It's a lot more adaptable. It makes the customer a lot happier in the end. So correct any errors found during compilation, link the program, run the program, correct any errors, rinse and repeat. Validate the results of the program. Does it do what it was defined in step 1? Let's check out page 23. Tying it all together. Okay, we're actually going to do this together, so it's listed here obviously, but just to show you, because you do have some problems to work through for this, even chapter 1. I'm going to take you through the creation of a Visual Studio project. I'm going to show you how to submit it, and then we'll kind of call it a day here with lesson 1. So tying it all together. Hi, it's me. Most programs that you have learned have 3 primary activities: input, processing, and output, but you can write a program that only has output. So in this case, we're not collecting any data from the user. We're just doing some processing and displaying some information to the output, in this case, the console window. You do have access to the sample program, so I'm told, in the Chapter 1 Programs folder on the Books Companion website. Again, the publisher is Pearson. Let me re-log in here. This is sort of the companion page for this particular book. You can go into student mode or educator mode. If you were in student mode, it would look like this. But I think once you go through and purchase it, if you even have the physical copy now, there's probably like a code in the back where you can go and download all the source code, the sample programs for the text. Okay, we're going to go ahead and run something like this, not exactly the same. And it says, once you've run the program, change the word me to your name to personalize the message. Then recompile and rerun the program. There's a couple things here we won't know maybe exactly what they do, but that's okay. We'll cover that in a lot more detail in future chapters. All right, as long as I'm here though, actually before I step out of the book, this is what the end of the chapter review questions look like. We are not going to be doing fill in the blanks. We're not going to be doing, like multiple choice. What we're going to focus on instead, algorithm workbench. No. Keep going. Fix the error. We'll do some of those occasionally, where here's a little code snippet. Can you identify by looking at it what is wrong, or what's the expected output versus what is the actual output? We're going to be focusing on the programming challenges. This is the meat and potatoes of the chapter. So for example, and this first guy here happens to have a video companion. So this should come with the textbook resources that you'll get once you register your book and go through all that process, solving the candy bar sales problem. This is going to provide you with some tips and tricks on how to solve this first challenge. So as an example, using program 1-1, so you can start with that. You may have to rewrite it, but that's okay because it's not very big. Starting with that as an example, write a program that calculates how much a student organization earns during its fundraising candy sale. The program should prompt the user to enter the number of candy bars sold and the amount the organization earns for each bar sold. It should then calculate and display the total amount earned. Hopefully not a big deal. You can obviously, again, take that program 1-1 and modify it to perform this given task. Now there's 4 problems here. Let us actually write some code, kind of. I'm going to show you Visual Studio. Just a quick tour here. So once you get it installed, you'll have access to Visual Studio 2022. And once you fire it up for the first time, you're going to see a window like this. You're probably not going to see any solution files over here. These are all C# files. Instead, for us, we're going to create a new project. And you can see some of the various types of projects you can create in Visual Studio. Some of them I know what they do and use them quite a bit. Some of them I don't have a clue. But for us, we're going to select C++ from the language drop-down here. And for all the programs we write in this class, we're going to be using the console app template. Not empty project. Don't use that. Use console app. Run code in a Windows terminal prints hello world by default. Let's select that. We'll hit next. And here's a key screen. So when we create a new Visual Studio solution, we have two things we need to basically name. We need to give it a solution name, which I would highly recommend calling it Chapter 1 in this case. So this is like the highest level project file that you're going to be dealing with. The program name is exactly what it says. So, it says project name. In this case, we're going to treat this as the program name. So for us, just with this demo, we'll call it the program name Hello World. Make sure you do not check place solution and project in the same directory. You can also take note of the location where it's going to save this project on your computer. If you're at an Iowa Lakes workstation on one of their computers, this probably should be like your H drive or your cloud drive if you're using OneDrive. Let me show you the structure of this. When I hit create, you're going to see exactly what this does. All right, so we have our first C++ program open here in a new tab, helloworld.cpp. You can find it over here in this what's called the Solution Explorer. This is where all your files and folders are going to be contained. Notice the solution is like at the highest level. Chapter 1 is the solution. Inside of that, you're going to have separate individual projects or programs. So we have a Hello World program. If you expand to source files, that's where your helloworld.cpp file lives. You can add, and this is how I want you to structure all of your work in this class, basically. You're going to have one solution for each chapter. Within the solution, you're going to have separate projects or programs. We have one right now. So if I was going to go ahead and work on candy bar sales, I would jump back over to Visual Studio. I would right-click the solution chapter 1. I would go to add, new project, and here we're back to our familiar new project screen. I'm going to again select console app. And now all I need to do is give the program or the project a name. And you can be like, there's some flexibility with what you call it, but I need to know basically which program this is. So ideally you might call it like assignment 1-1. It looks like hyphens are a valid symbol. So assignment 1-1, or I wonder if you could even call it 1-1. Looks like that's valid too. Create. Now, it's created another project under my solution. So I have two programs here, Hello World and 1-1. If I'm going to work on 1-2, I go to add, new project, create a new project for 1-2. A couple notes on this. You can see it's added quite a bit of comments for us. I'm going to delete those, delete that. You can change that template, by the way, so it doesn't automatically add them. We're going to be focusing in on Hello World here. Okay. Notice that the project or the program Hello World is sort of bold here and highlighted. I'm going to change this slightly. I'm going to add a bunch of exclamation points so that when I hit this run button, local Windows debugger, it's going to go through all the steps we just talked about. Compile, link, and run. And it's on the other screen, so I'll pull it back, and I see the text Hello World displayed in my console window. Press any key to close it. With all the exclamation points, by the way. Say I want to come up here to 1-1 and start working on it. So I double click the CPP file, pops open in a new tab. I go to run it. pull it back here. I still get the version that has all the exclamation points. So what I'm trying to tell you here is that when the project name is bolded, that's the currently active program or the currently active project. If I want to see this version of Hello World, I can do a couple things. I can right click on the program 1-1. I can go to debug, start new instance. Now I see multiple monitors working against me here. Now I can see this version of Hello World with a single exclamation. So again, that was right-clicking on the project, debug, start new instance. I did not click on this button. If I wanted to click on this button to run the thing, I would right-click this project. I would then say set as startup project. Now you can see Hello World isn't bold anymore. 1-1 is. Now when I hit this button, I can pull this over and I can see that I'm still getting that single exclamation. So what do they want us to do here? A couple pages back, just wrapping up. Print a message with your name in it. So let's do that. Hi, it's me. I'm learning program. So let's do that. And we need to include IOStream and using namespace. So we've included IOStream. We need to say using namespace std. You can see the IntelliSense or the autocomplete in action there as I'm typing. I get helpful pop-ups suggesting what I should type next. Because I'm now using namespace std, I can get rid of this std : and just say cout. Hello world, new line. I'll just say cout. It's me. I should put the comma. It's me, Kevin. Semicolon. That's something we'll learn about later. What is that slash? And then the single quote. And now, here's kind of what the book wanted us to do. Basically add a new line, put our name in there. Life is good. Okay, so here, for your assignment, which I will upload, I'm just kind of telling you sort of off the cuff here. In this first chapter, you're going to have four programming challenges. Candy bars, baseball cost, flower garden size, and flower garden cost. That means that you're going to have all four of those contained in the Chapter 1 solution. You can have other programs in here. You can have other projects. Like I have a Hello World. If there's a program from the chapter that you want to work on and like play with and modify and just try out, you can certainly include those here too. But when I go to grade, I want to have it very obvious which program is for which challenge. So again, I would call them like 1-1, 1-2, 1-3, and 1-4. You can have other stuff if you want to under there. You need to at least have 1-1 through 4. When we get to the next chapters, I'll be putting the demonstration programs, I'll be putting them under the solution like this. You don't have to if you don't want to. I'd highly recommend doing so, following along as I type. There is a certain way, like you get more comfortable with the programming language the more you write in it. Things like the curly braces, the parens, the angle brackets. That just comes with time. That comes with experience writing the C++ code. So the cool thing about these video lectures is you can pause as much as you need to. That's one of the benefits about doing it in this format instead of live. Sometimes students who aren't the fastest typers might fall behind. You're holding up the class for maybe a slow typer. It's okay. But in this case, you can pause the video and catch up if you need to. I know I'm a fast typer. Sometimes I get to talking really fast if it's something I'm particularly excited about or interested in. So just know you should be typing along ideally. Feel free to use that pause button as much as you need. Almost done. Okay, say you have all of your assignment programs in here, 1-1 through 1-4. How do you submit the thing? I showed you earlier where on your hard drive it was creating this project structure. If you don't remember, one thing you can always do is right-click on the solution. This is pretty handy. And open a folder in File Explorer. That will take you right to it. Something like this. Now, if I go up one more level, I can see here's the Chapter 1 solution. This is the highest level sort of structure for this particular project. Inside of that, I'm going to see subfolders. One subfolder for Hello World, one subfolder for each additional project, like 1-1. If you take a peek in the Hello World folder, and you dig deep enough, first of all, here you can see the CPP file. Don't ever double-click the CPP file to open it. If I drill down deeper, you can see eventually somewhere in there is the exe file. I may not have it set up quite right for that. That's okay. If you wanted to open this thing again, so say I close it, take a coffee break, come back, I want to work on it again later. Like I said, do not click on the CPP file. What you need to do to reopen this later is, first of all, you could either just fire up Visual Studio, and in your list of recent projects, you'll see the SLN file here. Again, that stands for Solution File. You could open it there, or you could come to the folder itself, double-click the SLN file, and it pops open with all your projects still structured exactly the way they are when you left them. Okay, how do you submit it? When you submit things to Canvas, you can only submit things one file at a time, which is kind of annoying for us because we have lots of files and lots of folders. So what I'm going to have you do is you go up one level, and your path here may vary, of course. Your solution, your Chapter 1 folder may not be in the exact same folder as mine. But what I want you to do to submit it is right-click on that Chapter 1 folder, send to compressed zipped folder. Oh, you're making a fool of me. Let's see. Let's try that again. File not found or no read permission. I've never had that not work before. What about if we do 7-zip? Most of you can probably ignore this because your send to is probably going to work. Let's see. Here we go. Zip. Oh, it's telling me that oh, that's why. Let me cancel this. Duh. It is refusing to zip it up because it is still open. So close it first. Then we can right-click. Now you guys can follow this. Right-click the folder, send it to compressed zip. It's going to go through its compression. And then this single zip file will be what you submit to Canvas. Again, I don't have the assignment created and uploaded yet, but I will. There will be a Dropbox there that will accept only zip files, by the way. So you won't be able to actually submit the CPP files, and I don't want them. I want your zipped Visual Studio solution, which contains all 4 of these programming challenges. Okay, so that's what you'll go ahead and submit. I'm used to asking if there are any questions at the end of the lesson, but there's nobody to ask. So I guess I'm talking to myself. That concludes Chapter 1, just a basic introduction to computers and programming. Chapter 2 next week will become much more interesting as we get into actually writing some more interesting programs. I hope you all enjoyed this online format. It's kind of interesting for me, never having done it before. usually used to the face-to-face sort of lectures and lessons. So if there are any tips that you have for me that would make this easier for you guys as far as learning, let me know. I'm totally willing to adapt as needed to make you guys as successful in the course as possible. So thanks for sticking around here for Chapter 1. We'll get into Chapter 2 next week. In the meantime, be on the lookout for the assignment file posted in the assignment section of Canvas. You'll just see a Chapter 1 assignment there, and that's where you'll go ahead and submit your work, your single solution file, your zipped up Visual Studio solution. Thanks so much for watching, and we'll see you next time.